folks, welcome to another exciting episode of the Performance Series. In the last episode, episode 2, this being episode 3 obviously, we talked a little bit more about how to get perfmon collecting some data for you. We briefly covered black boxes, but we mostly and most importantly talked about how to get a data collector set started, how to make it circular if you wanted to, put stop conditions, covered all the little buttons and bells and knobs and switches that go into the various data collector sets and data collectors themselves, which are these and these inside of here, which is still running. And so we also then covered a little bit about how to manage with command prompt, how to manage using logman. So we had some examples here on how to create a counter set remotely or locally using a command line, using a nice little text file full of our favorite counters. And anyway, so in this episode we're going to continue on with that a little bit. We're going to talk about how to load up a capture. We're going to talk about how to get your values into perfmon, and kind of continue on with the elementary pieces to data analysis using perfmon. So without further ado, on we go. The first thing you need to do if you're going to look at a data collector set is you need to not be collecting data on that data collector set anymore. Don't ever try to open one that's running. You could, it's sitting there, but it's not complete. Remember, we talked about how perfmon doesn't really always have, oops, that's not the one I wanted. There we go. It doesn't always write to the disk. In fact, you can see it still hasn't really written anything to the disk since the last time we looked at it, which for you was probably another day, which for me was actually only about 10 minutes ago or so. So I kind of fooled you there. Anyway, so if any of you have been writing stuff in the comments saying, Chris, do this, Chris, do that. Oh, Chris, you screwed up so bad. Yeah, I haven't seen those yet because this is the future. Actually, this is the past. You're in the future, which is kind of weird when you think about it. But yeah, so not getting too deep here. The data collector could be double clicked. You should never do that, especially when it's running. But even when it's not running, don't do that. Don't collect it. I wish that Windows team had not actually associated the open with perfmon. It should not be, because you shouldn't open it that way. It's bad. What you do is you stop the data collector set. Follow me here, because you're going to make this mistake. Don't make this mistake. Don't be old me, be new me. Stop the data collector. Once it's stopped, it's now safe to open it, but we don't double click it because well, you know what? I'll just show you what happens. You double click this thing and you get every single counter all in one graph, and it's an absolute mess, right? This is not as bad as it could be because I didn't put 7,000 process counters in here alongside it, but this thing gets messy. The proper way to open these is to go up here to where we were before in the Performance Monitor tab, and there's this little blue cube. So when we click the little blue cube, it opens up this window where we can open log files. We click add, we go out to this PC, we go to, good gosh, can't scroll today, C, we go to perflogs, admin, wherever your thing is. We can go ahead and hit the time range because this is a good way to make sure your data collector set's not corrupt or still running. If you get time in here, you'll notice that it's got a begin and an end time, and you'll know that you got good stuff. If it's not, then you've done something wrong. It's probably still running, or it's corrupt, which doesn't happen as much these days as it used to be. Corrupt counters used to be actually fairly common, not so much anymore. So you click OK, here's where everybody gets kind of lost, because there's nothing here. I just loaded it up, there's nothing there, and that's expected. There is actually something here, and it's kind of important. Down here, people don't tend to look down, they look up. People tend to look at pretty things in graphs, not numbers. But I'm going to teach you that the graphs and the numbers and the stuff down here below is more important than the stuff up here on top. So anyhow, what you do is you click the green button. So you'll notice that this is a little bit different than yesterday's lesson, because yesterday we had kind of a local host thing and we had a ton of objects. This is different. It's actually giving me the machine name this was captured from. This is handy if you have multiple captures loaded and you want to swap between multiple machines or multiple captures on the same machine. You can do that up here, and then you'll notice the only objects that appear are the objects that we loaded in the counter. It's only showing you that because that's all the data that you gathered, right? So logical disk, you can see that we have an instance for C, and we have all our little counters we wanted to see. So we've got our read times, and we've got our write times, and we could click those in there, and let's say that we wanted to see like how much RAM was available megabytes, and maybe percent of committed bytes in use. We could toss that in there. We're not going to get process analysis started here because you always save that until you figure out what is actually broken. And so we'll skip that and we'll go ahead and do percent of processor time, and I'm going to go ahead and do total initially. You probably would not want to do that. You want to look at all instances. Actually, you could just click and shift click or control click and dump those in. Well, let's just go ahead and do it that way, because that'll tell you whether or not you had one single threaded process hung at 100%, which also might be a key indicator. And yeah, let's just go ahead and do that. And I click there and bang. This is a little easier to read. So this is what it looks like by default. I know it had the big black lines on there a second ago. That was because I had something turned on that I didn't mean to have turned on yet because I wanted to show you. There are a couple of very important things to notice here. Up at the very, very top of this graph, when we look up there, you'll notice there are actually some counters up there. They're glued to the ceiling. Why would they be glued to the ceiling? Because the graph scale right here is at 100. The graph scale is 0 to 100 and modifiable. The counters are at a different value and are either higher than 100 or they are lower than 100 and showing up in the graph. I can hover over the points on the graph and it'll tell me actually what the counter is, and then if I hover over the point itself, you'll notice it switched, and now it's actually telling me at that exact moment in time average disk per second read was at, let me hover it again and give it a second, it'll load the rest of the data. Maybe let me try a different point here. There we go. Average was at 56 milliseconds, and the exact point in time was 12:46:30 p.m. Okay, so hovering over the different points on the graph can get you data. If you're getting lost with all of the different little colors, one of the things that's a really key trick is this highlighter function. When you click the highlighter function, whatever you're selected down here in the bottom will turn a very dark, thick black color, so it's easy to pick it out. You can also change that selection up in the graph itself. So if this little red one that we were looking at a second ago was more of what I wanted to see in focus, I can click on it. Click on it and it becomes the highlighted piece, and it jumps to that part down here in the lower section. So that's highlighting. This can be done just by scrolling up and down with your mouse key. So I'm scrolling up and I'm scrolling down, and the one that was above everybody else was this available megabytes. So there's two different ways we could get this to show up. One of them is to change the scale of the graph, and the other is to change the scale of the counter. It's very important to know when to do which. In this case, because we have a whole bunch of different counters that have different types of base values, we would scale the counter to match the graph. If we had all of the same types of counters, like process, disk I/O operations per second, and it was all of the different processes, well, that's every single process on the box and his I/O operations. So if I scale the counters on those, they're all going to fit on the graph, but they're going to be completely out of balance, right? Some of the exact same counters will look bigger than the ones smaller than them because you had to scale them up. Let me explain. If I right-click on the graph itself and I say Properties to the graph, and go up here and start adding zeros to the vertical scale, like add a 0 and press apply, and you can see now I can see a little bit of a breach coming down, and then maybe add another 0 and hit apply. Okay, we got it down there. We can see that maybe 2000 is actually a good value because we saw where it landed on the graph, and there, bang, right? So I pulled him down, but what did I do? I sucked everybody down so far I can't even see them. Well, why is that? Well, it's because he's got a huge value and these other guys have got very small values, right? And we want to kind of get them all on the same page so we can see them, right? right? So I'm going to go ahead and put the graph back to 100 because, well, that's where we want it to be because it worked out really good for a lot of these other counters, right? They fit. So what I'll do instead is I will go and find the available megabytes, right click them, and scale the selected counter. And I could even do that with everything. I could Control A, right click, and say scale selected counters, and everybody's going to get scaled. And now what I can see is available megabytes down here. Now you might be wondering, okay, well, how does that, is that good? Is that bad up here on the graph scale? You know what? I'm not sure that the mouse is showing up super duper good on this. So what I'm worried about with that is that you can't actually see what I'm picking. So we're going to go do a trick real quick. We're going to sidebar. I'm totally getting off subject, which is like I've never been to a YouTube school or done any YouTube videos, but I've watched a lot of YouTube videos, and I think that probably the one thing you don't want to do that I see other people do a lot is kind of get ADD about what they're working on, and so that should be like your no-no. But I'm going ADD right now, so here we go. So live.sysinternals.com. We go to live.sysinternals.com, and looky there. Every sysinternals tool available to run immediately from the website by just clicking it and then agreeing to the EULA, and then bang, it'll be running. I mean, everything's in here. PS Kill, you've got your process monitors and process explorers, etc., etc. All right, so we're going to get Zoom it because I need you guys to be able to see the mouse. And this is actually a virtual machine because we're going to be doing some really terribly unholy things to this VM later. And I don't want my actual box that I'm using in the recording to suddenly lock up because I ran this thing completely out of RAM, because that would be bad. Because, yeah, obviously. So what we're going to do instead is we're going to do terrible things to this VM. Alright, so here we go. We've got Zoom it running. I should be able now to do things like Control 2, and I can do the scale of the graph discussion like that. So this means nothing, believe it or not. I can alleviate all of your confusion about where these things land on the graph and whether the scale is good or bad, and going up is bad or good, or where if it's getting too close to the top. It doesn't mean a thing. So that's kind of the next thing we need to talk about is, where are the values supposed to be? Well, they aren't listed in perfmon. You just need to know them, and that's the whole point of this class. What you can control is kind of the vertical scale. So vertical scale of the graph we already looked at, but the vertical scale of the actual counters is kind of this little thing right here. Whoa, I forgot to push Control first. I slashed a big old mark on it there. So this little piece right there. Each counter's got his own default value. We adjusted the counter value for available megabytes here down to 0.01. His default was actually, I think it was 1. But each one of these has kind of a decent starting point that's kind of been guessed by the developer of the counter what it should be. Obviously, all your percentage counters are at a 1 scale, which is great as long as your graph is at 100. But if you've adjusted the graph, a percentage counter is no longer going to be looking like it should. I'm at percentage committed bytes in use, pretty much 40%. What happens if I come up here and put 1,000 on that graph, right? If I put 1,000 on the graph, well, the value of the percent of committed bytes in use didn't change. It's still an average value of about 40%, and so he's showing on the graph down here in the 40s. You can't see him anymore all that good. So if I right click and scale him, he'll come up here. See what it did? It added one number to the scale of the counter. It's now 10 instead of 1. It's just a visual multiplier. It's incredibly important that you understand the difference, because a visual multiplier is different because you don't want to skew your data. That would just be wrong, right? That'd be all kinds of wrong. These values didn't change, right? Average, min, and max values are exactly the same as they were before. All it did was it pushed it up on the graph where you could see it. It was down here. Now it's up here. So what you did was you just said scale the counter so that I can see it better on the graph. That's all you're doing. That's as complicated as that gets, and that confuses the living heck out of people. And if you don't get anything out of this particular part of the lesson, and other than that, that's probably the most important one, is understanding the difference between scaling the graph, scaling the counters, and making sure that you're understanding that the min, max, and average value of these counters are all the same values, that this stuff here does not actually get impacted by things that you do to the graph. This is so you can see it. The computer could care less what things look like on a graph. You see things and make visual patterns with them, and so it's very useful to provide yourself with these visual patterns because you need those to be able to do analysis. Like if I saw available megabytes trending down, would that be bad? Yeah, that means I'm very quickly running out of RAM, so I need to be able to see that on a scale. If it's scaled up into the top of the graph where I can't see it, then I can't see a visual pattern. So I want to get things onto the graph in one way or the other. So that's why we would scale things and put them all on the page so that I can see them together, so I can see stuff happening. You'll notice there's a kind of an inner of correlation right here where available megabytes and committed bytes in use kind of seem to take a bit of a complementary pattern to one another, and that was right during that time frame right there and there. Ooh, not that one. You can see they kind of had the same bump, but in different directions. You might be saying, well, why do they bump in different directions? Well, percent of committed bytes in use is a percentage value, meaning in use, whereas if you think about available megabytes, that's a type of counter that's measuring a value, and in this case it's measuring a value of what's left. So naturally when this one goes up, that one's going to go down. So they're sympathetic to each other. Okay, so you just saw me do another trick that is kind of important to learn, and that's called looking at the time scale. And what we do to be able to get to the problem, we can see just kind of visually, without even looking at all these other counters, something was kind of going on right during this period of time that did cause some of our counters to do interesting things that they weren't during other parts of the capture. So what you can do is kind of pull this across here and then right click and zoom to, and now we're only looking at periods of data during that time. Now what's really interesting about that is all of your counter sets down here have adjusted to that period of time. Right? So our percent of processor times average is different now because it's only showing me the average of processor time on these two cores during the period of time in which I just moved into. Right? So that's changing the time of the graph. There's another way to do this, and that's inside the blue cube. This used to be the only way to do it. You notice that when I zoomed in, these two little guys kind of changed their pattern just a little bit right here, whereas before they were all the way out. You can slide your time rule in here using that method as well. So I can move that out and click out. So now you can see that this little slider bar right there is adjusted. I can move it this way as well and zoom to. Or to get out, you can double click up like that and it pushes everything out. Right click, zoom to, and you're back out. So that's kind of an important task to learn, because what happens is you have a problem in this area. You want to zoom in and look at what all was going on during that period of time and not be distracted by everything else where things were happy. You need to know what a server's what its good looks like and that's important because you got to have some sort of a benchmark on what the server is showing you during happy times versus what it's doing during not so happy times like this. So that stuff becomes important when you're looking at a time frame. Usually you already know when the point of failure was. Somebody tells you at 2 o'clock in the afternoon yesterday it just completely went off the rails, so you can go look at 2 o'clock. Other times you may actually have to, you get a description that's like, hey, this server was just up and down all night. It was available, then it was sluggish, then a big lag, and then it came back. Need to know what's going on. And if that's the case, then you may have to look and find the patterns yourself. And usually using a method like this gets you a pretty good idea of when the problem was, what the problem was, etc. With all this talk about graphs, though, it can get a little bit confusing as to what's important to be looking at here. graphs are good for seeing things like this. We see a period where this processor went up and it went down. You can see that data easier than if you were looking at this from a CSV. If you were looking at this on a spreadsheet, looking at the data going up and then down again, you'd probably take that spreadsheet and turn it into a graph anyway, because it's easier for you to see patterns when you're actually looking at something visual like what's up here. The most important thing on this graph is not actually this capture is not the graph at all. The most important thing that we're seeing here is actually that piece that I alluded to a minute ago, and that is these three little guys right here: average, min, and max. So for every one of these counters, there is an average of the entire time period that this was running, a minimum value, and a maximum value. Now, different counters will have different things that are important to them. For instance, the available megabytes, the minimum value is probably the most important thing that's in there, because you might suspect that your server ran completely out of RAM, and if it did, the min value will be close to 0, right, or just really, really low. Whereas maybe percent of processor utilization, that's going to be really important when things get up high, right, because we're looking for close to 100% or pegged at 100% for extended periods of time. And in medial values, there is on both of those, you're going to visually see it hit the bottom or hit the top of the graph, but not all counters are that way. In fact, most of them are not. You need to know actually what is good and what is bad. So this is average disk per second, right, that we're taking a look at right here, and that average is at 9.019, and then minimum is at 0, and then maximum is at 3.216. So what the heck does that mean? Is that good? Is that bad? It's kind of hard to look at the graph and know. It kind of looks like it went up high on the graph, but Chris just told us a minute ago that where it is on the graph doesn't necessarily mean anything, and he can drop it anywhere he wants on the graph. I can make this look pretty, I can make it look ugly. You need to know the values, and I'm going to give you guys a chart that you can use that is going to be capable of kind of telling you where your thresholds are for problems. For instance, average was at 19 milliseconds. And this is a counter that actually isn't real intuitive by knowing it right off the visual piece, because we don't know that. What does that mean? 0.019. What the heck does that mean? It just says average disk sec write. What do you do with that? Okay, this is why we are covering it in the class, because this is a very important counter. You will need this counter. The read and write disk counters are your primary indicators, which we'll cover in about 3 episodes from now, will be the disk performance primary indicator of an issue. And knowing that 0.019 means 19 milliseconds of latency is a key to understanding where your problems might be. In this case, specifically, anything over 15 milliseconds, and you don't have to write all this down now. I will cover the disk performance in a later date, but right now we're just kind of going over what is this, what is this whole perfmon thing, and how do we click buttons on it right now. So 19 milliseconds is getting into problematic. God, somebody is really blowing up my phone over there. 19 milliseconds is over what we would consider a warning threshold of 15. So when we see the value go up over for a period of time over an average period, we averaged 19 milliseconds. We also had a maximum value of 3,216 milliseconds, which is just horrendous. It's just terrible, because your floppy disk drives average about 600 milliseconds, which means that points during this, maybe they were just small points. The maximum value means at any data point on the graph, this was the biggest value we picked up, which is why a lot of times average can be a lot more important, but it's also nice to know that at some point we spiked here and that we need to probably look at that, because over 25 milliseconds is where I warn for extended periods of time, and that's why averages are important, because, well, that kind of tells us extended period. It's also why we do things like zooming. So, it's fairly obvious from looking at that this interesting point in time right here actually was right there where we saw some pretty big data jumping up, and we go back to our read and our write times, you'll notice that the values just changed. So that's throwing our average in right there, our average is now 45 milliseconds during this 3-minute period of time. So for actually, it's probably a little closer to 2.5 minutes, 2 minutes. We had data points that were over the charts of the graph. We were up there as high as the 3,216 milliseconds, and we were averaging 45 milliseconds. So if your users had complained about slow performance during this period, which if I will have cut the part of the video where this happened. This actually happened when the first time I tried to load Task Scheduler and pull that up, and it actually hung. So I think it even crashed at one point, but it's because it's a VM on a fairly underpowered system, so we actually expect there to be performance issues, and I picked it for that very reason, because we get interesting things happening live that you have trouble sometimes creating in the real world. So that's why Zoom is very good, because you can get the actual time frame that was important to you right here and in this little time slice, because that's probably where your users were experiencing the most data. So that's the zooming, that's understanding average and minimum and maximum values, and every counter again is going to have something more we care about. Percent of committed bytes in use, for instance. We're really kind of more carried about the maximum there, and percent of processor time is the same thing, and available megabytes again, if that had hit 0. Minimum is much more important to us. Our minimum here was 860 megs. So that's average, min, max, and chart zooming. But nevertheless, never mind that average, min, and max is some of the most important stuff you'll catch yourself looking at the more you do this. The graph is still important, because the graph shows you things that you can't really pick up by just looking at the average, min, max, and that's going to be things like a decreasing line in a counter, or an increasing, or humps showing like resource spikes, or even more importantly, when we see something that went bad and we're looking to find out why it happened. So I'll give you a couple of examples. This wasn't the greatest capture to do this on, but that doesn't matter, because this is just getting kind of our feet wet here. So we want to get rid of some of this stuff. So let's pretend like the biggest problem we were concerned here with was let's just say processor, because that's really one of the easier things, right? So let's just say that we were concerned with why the processors were sitting here at kicking at 40 and 60. Obviously those aren't bad percentages, but it won't matter, because we're still going to cover the process anyway. So we need to clean up the rest of this graph, right? So if we've decided that processor was the issue, well, we don't really need memory counters, and we don't need disk counters in here. So I could either hit the space bar while it's selected, like that, and it just turns those counters off and leaves me with my percent processor time counters, or I can just go up through here, kind of hit the red X and delete them, right? So if I want to know what process was causing the most processor utilization, all I'm going to do is I'm going to decide, first of all, when was it that I was really concerned about processor utilization, and then I'm going to zoom into this. So now I've got kind of a good view, and now that I'm looking at this, I'm actually kind of thinking that maybe right through here was kind of my problem, so I might zoom again, and now I'm going to go dump in the process counters, but not all of them. It doesn't make sense to add them all in there, because really, if we're looking at percent of processor utilization, percent of processor time looks like the most valuable piece. And I'm going to go ahead and dump in all instances. I could do all instances, or I could click here, run to the bottom, shift click there, and add. The only thing, if you do all instances, you need to remember is once you've dumped in this massive amount of data, is go find total and delete it, because that's not going to help you in this case. So here we go. All right. Obviously, in this case, we don't have to scale graph. We don't have to scale counters, because everything's on a percentage basis. So this is a really good example of starting out. Because what do I mean by that? I mean, we are talking about a 0 to 100 graph with a 1-to-1 relationship in a percentage counter. Percentages don't typically go over 100%. And in this case, well, The processes shouldn't either, and you would think that'd be accurate, but it's actually not. When it comes to processor utilization, you'll find with process analysis, they can be at 200% or they can be at 400%. Why? Because, well, you got multiple processors, so they could be jumping up over the top of the graph. In this case, they're not, so that makes it easy. It's real cool. We still got our little highlighter here. We should take a moment and take the things that we are concerned with. In this case, the processor time for processor 1. Let's just say he's one we're really concerned about. So let's right click him, go in here to the properties for him. We're going to give him a nice bright red thick line, and then we'll go to the other processor and we'll give him a nice bright blue thick line, and then now they're kind of quasi already highlighted. Now, what you can see here, if you're looking close, is you can see that we've got kind of a bit of a correlation here, right? There's a pattern of the processors going up and down, right? And we've got some patterns of some processes going up and down too, right? So those are sympathetic counters. So if I were to highlight some of these and look at them, we can see perfmon was actually chewing up some data. Well, we were unloading counters, unloading counters, and doing all sorts of stuff with perfmon. So that shouldn't at all surprise us, right? And it's kind of right in line with the stuff we were doing. I mean, it goes up when the processors are going down. It goes down when the processors are going down. I mean, sure, we got some other spikes that are obviously sympathetic to that. So you can see this this kind of went up and down about the same time. Lost track. Let go of my mouse. There we go. And he was SVC host number 4, which doesn't tell us a whole lot about what that SVC host might be, but I'll show you a trick about SVC host is and their number multi-numbers on another little chapter that we'll go through. But at this point in time, this actually, you know what, we'll just go ahead and talk about it real fast. I'm going to have to wrap this episode up because we're going a little over my normal target time per episode, but I showed you process ID counter. Well, that's why you might need this, because perfmon will come through, and even though we see SVC host number 4, there's no such thing as an SVC host number 4. If I were to go in here to Task Manager and look for SVC host number 4, where's that going to be on? I can go here, sort by name. Let's go find SVC host number 4. Which one's number 4? Which one do you guys think's number? You're not going to know. You're just not going to know. But if you captured the process ID counter, in other words, the ID process counter, which for some reason we named backwards, and I'm not really sure why, we could simply load up the counter for that, and then we'd know which one it was. And then we could go and look at Task Manager and see which one it actually was that was causing it. What does it do? And then look at it live, and that could help us there. So anyway, what were some of the other ones that were kind of... So this is another sympathetic counter. In other words, the processors go up, and this is the process that did it, that caused it to go up. Over the entire period, though, we were mostly concerned with that. This means that in this case, perfmon was the guy that was causing the most trouble, which obviously we pounded on it and kind of made that happen. So that we're not real fooled by that. And processors never really got up super duper high. But if we were actually on the case here, if we were actually, let's pretend like, wow, this is 100% right there. Let's make these look ugly. It's like, I did that completely wrong with too many zeros. Let's want to do that. Like, now it looks ugly, right? And we found the perfmon, right? He's the culprit. He caused this issue. He made our processors go way, way, way too high, and peak out. So that's why you need patterns. You need patterns because you need to be able to see a correlative condition. There are other times when that's not quite so much of a parallel line. Why did I say properties? Zoom to, please. And we'll talk about that real quick. If you remember when we had these loaded up here, we saw that memory available megabytes had a bit of a dip. And so if I scale him down so I can see him, because again, that's why we scale these things. We need to make sure that we, where's it at? Scale, selected counters. And we didn't scale it quite enough. So let's scale it to 0.1 and maybe 0.01. I'm going the wrong direction, aren't I? No, I'm going way the wrong direction. Yeah, too many. We'll get it right. Maybe just a little more. Will that go over the top? Now, there we go. Okay, perfect. So now we can see that there was a dip in memory. Let's imagine for a moment, and we'll have some real examples in the memory module. I'm trying to prove a point here. So we'll zoom in here. We'll see that we took a dip in the memory. We got down to 860 megs of memory. If we were trying to do a match to a process, we would be looking at, since this is just RAM, we'd be looking at the working set of all of our processes and coming in and trying to figure out who it was who was taking that up. Again, we're going to dump the total one because it'll be the biggest one on the graph. This is another little method here where we want to not scale the selected counters, because they're all working set for the processes. If I scale them, they're going to go mess all over the place, and we're going to have big ones looking bigger than little ones. In fact, let's just do it so I can show you just how horrible this does. I can make these all fit in the graph by going scale selected counters. Now they're all here. I want to think, oh, he's the biggest one right there. But if you look at him, look at how his scale is. Look at this scale down here. This is a horrendous number just to get it all to fit, and you can't undo this. Once you've scaled all the counters, it's scaled. So the only way to fix that is, see how every one of those is scaled differently, making them appear like they're, problems when they're not, or little bitty but they're really big. So don't scale similar or like processes on the deal. Scale the graph out, and that's what we're going to do right now. Okay, virtual bio working set of all these processes right here. Little tip, we can shift click and we don't have to go looking for total and dump it. And I need to be able to look at everything on this graph. So we're going to add a 0 until we get this thing to climb off the ceiling. And we went too far, and that's good. So it looks like 20 or 1500, maybe 1700. Let's say like that. Should get us a nice view of the graph, and there we go. And I apologize, I've gone a little over the time I would normally do for this. Now I need to get him back up here because we scaled him way down and now we can't see him no more. So we're going to write, and we're just going to scale him just to get him up here, right? So what we're now looking for is a process, and again we'll go ahead and change the width of his line so he stands out nice and pretty for us as we scroll through here. And another trick is I can just sit here hitting delete when I see processes that are all down on the bottom and obviously not at all related to this. Or I can even hold down the shift key and start going through here relatively quickly. And I might want to leave those two there, kill those. And let's go through the rest of this. None of those guys seem to have a relation. That one sure did. So let's leave him. And let's keep on going. And do, and boom, and what do we got? Okay, so what we got now is we've got like 3 different processes. Now, would we expect that these are directly related? And oh, this is really interesting too. Really quick, I want to have a call a highlight out that we have an explorer and an explorer number 1. You would see that on a terminal server or in a server where people are going to be remoted in a lot. But why in the world would we have an explorer and an explorer number 1 here? So what that means is we had an explorer process going, and he had a pretty good amount of memory being taken up, or whatever happened to him. And maybe it was memory, maybe it was something else. In this case, it just got locked. It crashed. You can see this. This is a perfect example of a process that has crashed and regenerated. So explorer crashed. It totally tanked out on us. I was planning to cut that part of the video out. I may leave it in now because it's a very good example of what a process looks like when it crashes in perfmon. A new explorer.exe got spawned, and it is now called Explorer number 1. Perfmon appended that. It wasn't really a process called Explorer number 1. It was just an appended name. So what we had was an increasing amount of memory here, and then we had a total crash out, and then the new Explorer kind of picked up where the old Explorer was going on there. At the same time, we've got these other processes that seem to have kicked up, and he sucked up some RAM. We had this one over here. Oh, wait, that's Explorer. So he is not in a direct correlation to the loss of, I mean, these Explorer guys are not in a pattern that make me think that the memory being consumed is being consumed by them. Even though they do seem to be consuming a lot of memory, they're not exactly related to it. That guy, he's got a really good pattern, especially right in this area right in here. If I were looking for something that were consuming memory, I would do that, but they're not parallel. Why are they not parallel? Because one counter is talking about available megabytes. The other counter is measuring how many megabytes of RAM we're actually using up, right? The working set of a process. So this is going to be an inverse counter. And you need to be able to understand that sometimes you're looking for something that's parallel and sometimes you're looking at stuff that's inverse. And that's really the big lesson that I want you to know about why you need to keep these on the graph. You want to see this now. I'm pulled back. You can really see what's going on here. I suddenly consumed a lot of RAM right about in that area, and not surprisingly, the available megabytes dropped in pattern with that. And when he finished with whatever he was doing, the RAM kind of went back exactly, back to kind of a normal perspective right there. So that is a perfect indication of a real world inverse counter. You can see this. Computers can't see this. You have pattern recognition. You have the ability to look at this stuff and be able to interpret kind of what's going on. And that's why you want your graph to be working. So right. So that was the main point I wanted to make as far as being able to keep it on the graph and be able to make patterns out of what you see. And that's really about probably all that we want to cover in this episode. I've definitely gone about 15 minutes longer than what I had intended, but we got some extra good stuff in here, so I'm glad that it worked out the way it did. That crash in the middle certainly we'll probably find a way to leave that part of it in, even though it caused some weirdness in there. But anyway, I'm rambling at this point. Sorry, guys. This has been Chris with Microsoft. As always, thanks a ton for watching. If you did find anything about this useful or interesting, please give me a quick like, and feel free to subscribe to my channel as well. That way you'll get updates anytime I post a new video. Also, my blog is at 9z.com. It's super easy to remember, just the last number and the last letter.com. That's got links to my Facebook, my LinkedIn, my Twitter, my TechNet blog. And again, as always, thanks a ton for listening, and I'll see you guys in the next episode.